Hello and welcome. Today we're diving into a really cool question. In a world just swimming in text messages, articles, and social media, how do computers, which, only really get numbers, make any sense of our language? It's a puzzle that's right at the heart of modern AI.
I mean, think about it. A computer gets math. It was built for it. But language? Language is messy. It's full of nuance and context. So how do we bridge this huge gap between the pure logic of a machine and, well, the beautiful chaos of human words?
Well, the secret, and it's a pretty brilliant one, is that we don't really teach the computer our language. Instead, we translate our language into the one thing it already understands perfectly: numbers. It's all about transformation, and it's the foundation for pretty much all modern natural language processing.
And there's an actual name for this magic trick: feature engineering. This is the art and science of turning raw text into what we call numerical vectors. And that's just a fancy way of saying long lists of numbers that a machine learning algorithm can finally grab onto and work with. This is the crucial first step. So where did we even start with this? Well, the first attempt was probably the most obvious idea you could think of. We just started counting.
The first major technique is called the bag-of-words model. And it's a great name because you can literally imagine tossing all the words from a sentence into a bag. You shake it up, and all the grammar, the word order, the structure, it all gets jumbled. What you're left with is just a word salad, where all you know is what ingredients are in there and how many of each.
The process itself is pretty simple. First, you build a master dictionary, a vocabulary, of every single unique word you have. Then, for each sentence, you create a list, a vector, that has a spot for every word in that master dictionary. And finally, you just go through and count. Did the word "the" show up twice? Okay, put it 2 in its spot. Simple as that.
But here's the problem, and it's a huge one. Take a look at these 2 sentences. The king defeated the queen, and the queen defeated the king. To us, those have completely opposite meanings. But to a bag-of-words model, they're exactly the same. The same words are there, so they get the same vector. All of that crucial meaning from the word order is just gone.
So clearly, just counting wasn't going to cut it. This led to the next big question. What if not all words are created equal? What if we could figure out which words are actually important in a sentence and give those more weight?
And this brings us to something called TF-IDF. It's a really clever upgrade that scores a word's importance on 2 things. First is term frequency, or TF. How often does a word pop up in this one document? The more it does, the more important it seems. But, and this is the key, the second part, inverse document frequency, or IDF, keeps it in check. It asks, how rare is this word across all the documents? So a word like photosynthesis is pretty rare. It gets a high score. But a word like the is everywhere, so its importance score gets dialed way, way down.
But even TF-IDF, as smart as it is still just a fancy way of counting. The real revolution, the true breakthrough, happened when we stopped counting words altogether and started trying to map their meaning.
This is where the idea of word embeddings comes into the picture. Forget counting. Imagine creating a giant, multi-dimensional map, kind of like a GPS for meaning. And on this map, every single word gets its own specific point, its own set of coordinates.
Now, the logic of this map isn't random. It's designed so that words with similar meanings end up close to each other. So on this map, you'd find king near queen, and apple would be near orange. But king would be very, very far from apple. Proximity equals similarity.
And this is where it gets absolutely mind-blowing. Because these words are now just coordinates. They're vectors. You can do math with them. The most famous example is this one. If you take the vector for king, subtract the vector for man, and then add the vector for woman, the result you get is incredibly close to the vector for queen. Just think about that. The machine has learned the concepts of gender and royalty just by seeing how words relate to each other. So, to put it simply, this was a total game changer. This approach lets machines capture these really deep relationships between words, even understand analogies. These dense, information-rich vectors became the fundamental building block for pretty much all modern natural language processing. But there was still one major hurdle left to clear. A problem that even these amazing word embeddings couldn't quite solve: context. Just think about a word like bank. Are you talking about a riverbank or a financial bank?
The word is identical, but the meaning completely changes depending on the words around it, and that's a huge challenge for a machine.
And this is exactly where older models like Word2Vec fall short. Whether you're sitting on a riverbank or taking money out of a bank, Word2Vec gives the word bank the exact same vector. It has no way of knowing that the meaning has totally shifted based on the sentence. So how do we fix this? Well, this is where the modern giants of AI enter the scene. Models you've probably heard of, like BERT and GPT. These are all built on an architecture called the transformer. What transformers do is just genius. They create what we call contextualized embeddings. So instead of having one fixed vector for bank, a transformer looks at the entire sentence around it and generates a brand new, unique vector for bank that is tailor-made for that specific context. The vector for riverbank is now totally different from the vector for financial bank. Problem solved. Okay, so we've seen this incredible journey, from simple counting all the way to complex contextual understanding. But how does a data scientist actually use this stuff day to day? Let's quickly walk through the practical workflow. It really comes down to a simple three-step process. First, you have to clean up the raw text. That's called preprocessing. Second, you pick your method and you extract the features. That's the encoding step where you turn the words into numbers. And third, you feed those numbers into your machine learning algorithm to do its thing. And that first step, preprocessing, is absolutely vital. This involves a few key cleanup jobs. You break text down into individual words or tokens. You make everything lowercase, so the and the are seen as the same word. You get rid of common stop words like a, is, or at that don't add much meaning. And finally, you chop words down to their root form, so running just becomes run. It's all about tidying up the data before the real magic can happen. So there you have it. In just the last few minutes, we've gone on this journey from a simple bag of words all the way to these incredibly rich maps of meaning that can understand the subtle shades of context. We've seen how machines learn not just to count our words, but to actually start to understand what they mean.
And that kind of leaves us with a final big question to think about. If our entire language can be mapped out like this, with words as just points in space, what does that let us do? What new connections, what new ideas, or even what new forms of creativity can we discover in these vast, uncharted territories of human language? Something to chew on. Thanks for tuning in.